Up to last lecture, you have come to know about the fundamental laws of electrostatics and magnetostatics. These laws were Gauss's law in electrostatics, the form of Gauss law in magnetostatics, Faraday's law and Ampere's law. Now you will study what inspired Maxwell to work on unification of electrostatics and magnetostatics. But before coming to Maxwell's work, let us go through one more equation, that is the statement of conservation of charge. It is named as continuity equation. It may be said that equation of continuity defines the electrical current in a system with a charge density. Suppose in a given volume tau, the charge is decreasing at some rate. Assume that we have no source or sink of charge in the system. This means that it has to go outside the region. Then the current I will be defined as the time rate of charge. As with increase of time, the charge in given volume will decrease, a negative sign is put in the expression. The amount of charge decreased per unit time has to go down as the flux of charge or the current through the boundary of the volume. So, the given equation can be written as this. Here, the current I is written as the closed surface integral of current density, and the charge is defined by the volume integral of volumetric charge density. Now, the volume integral and surface integral are two different types of integrals, and the surface integral can be converted into volume integral using Gauss's theorem. Now the comparison gives this equation. So there is no difference between this equation and this equation. So this is the statement of conservation of charge, and this equation is known as equation of continuity. Now let us discuss the inconsistency in Ampere's law, which inspired Maxwell to work on the concept of displacement current. This is the Ampere's law in differential form. If you take the divergence of this equation, you will get this. Now if you see this equation, the left hand side is 0 essentially, because the divergence of a curl of any vector field is 0 always. But right hand side needs not to be 0 always. The right hand side of this equation is 0 with steady state currents, but it is not the condition always. If the current is varying with space, then this equation does not hold. It is the mathematical inconsistency in Ampere's law. You can see the inconsistency in Ampere's law with an electrical circuit having a capacitor. Let us draw two Amperean loops C1 and C2 respectively inside the capacitor and outside the capacitor. In them, the loop C1 does not have any charge flow or the current through it because it is inside the capacitor, but the loop C2 does has a current I drawn by the battery in the circuit. Now the Ampere's law in integral form for both the loops reads this equation and this equation. Here I enclosed is the current drawn by this battery using the flow of electrons. Now if you bring these loops infinitesimally close, they must give the same result. But you can see it is not possible with the current form of Ampere's law, and this is another proof of inconsistency in Ampere's law. So there is a flaw in calculations by Ampere's law as the infinitesimally closed Amperean loops result for the different answers. This discrepancy in Ampere's law was removed theoretically by Maxwell by the introduction of the concept of displacement current. Let us discuss in the next slides the displacement current. Since the discrepancy in Ampere's law was at right hand side of its differential equation, it was that the divergence of current density J at right hand side was not vanishing in case of steady state current. To remove this problem, let us start with continuity equation, which says divergence of J plus time rate of charge density when added with each other gave 0. Using Gauss' law in differential form, we can replace the charge density with epsilon naught times divergence of electric field. And again, the order of differential with respect to time and with respect to space can be reversed. And this gives this equation. This equation says that albeit divergence of current density is not zero always, but the divergence of current density plus something is always zero. This extra term epsilon naught times del E over del T, which makes J divergenceless, has the dimensions of J as it is added in the current density. This extra term was called displacement current by Maxwell, and this is represented by JD. So, with this modification, Ampere's law becomes del cross B equal to mu naught times J plus displacement current epsilon naught del E over del T. This J is conduction current, which is the actual current by conduction of the electrons, and JD represents that varying electric field causes magnetic field even without an electrical current. This is converse of Faraday's law. This modification is very important, as without this correction one cannot talk about the electromagnetic radiation. Let us check how the modified Ampere's law is consistent with an electrical circuit having a capacitor. If it is correct, then the loops C1 and C2 both must give same value of current or magnetic field induction B. So we can use this modified Ampere's law with loop C2, where there is no JD, and this becomes line integral of B equal to mu naught I, where I is the current drawn by this battery. Now we use the modified Ampere's law in loop C1. For the loop C1, I is 0, but displacement current is not 0, and the displacement current density is epsilon naught times del E over del T. When this displacement current density is multiplied by the area, it becomes electrical current, and electrical current will be equal to epsilon naught times del phi E over del T, where phi E is electrical flux. So, for loop C1, the Ampere's law reads line integral of B is equal to I, which is 0, plus mu naught times ID, which is epsilon naught times del phi E over del T. Phi E is the surface area of the capacitor's plate multiplied by the electric field inside the capacitor. The electric field inside the capacitor is sigma by epsilon naught, where sigma is the surface charge density on the plates of capacitor. Sigma multiplied by S will then be the total charge on the plate of capacitor. So this whole equation will be mu naught times del Q over del T, or mu naught times I. This I is essentially the current drawn by the battery. So the modified Ampere's law gives the same value of magnetic field by both the loops C1 and C2. With this modification, all the laws got the same form, and the equations for those laws, including the modified Ampere's law, are called as Maxwell's equations. So Maxwell's equations are in their differential form del dot E equal to rho by epsilon naught. This is the Gauss law in electrostatics. Del dot B equal to 0, which says that there is no magnetic monopoles in the nature. Third is del cross E equal to minus del B over del T, which is the Faraday's law. And the fourth is del cross B equal to mu naught times JC plus JD, which is the modified Ampere's law. These Maxwell's equations are very important, as Helmholtz theorem says that provided a field vanishes very far from its source, the curl and divergence of it are sufficient to determine the field at any point of the question. And the Maxwell's equations are nothing but the divergence and curl of electric field and magnetic field. So, in this lecture, you have studied how Maxwell modified the Ampere's law to remove the inconsistency in its mathematical form and in the circuit with capacitor. and all four Maxwell's equations. In the next lecture, we will discuss about how the Maxwell's equations can be solved in free space and conducting medium.